The worst-case scenario for 3I Atlas seems unbelievable until you think about this possibility. What if it isn't leaving? What if the path we see as a simple flyby is actually a slow-down maneuver using technology we can't detect? Imagine an intelligence so advanced that copying natural space movements is easy. A civilization that can send objects into space disguised as comets, asteroids, or even space junk. 3I Atlas's incredible speed and unusual chemistry might not be random. They could be signs of deliberate intent. As it gets closer to the sun, hidden systems might be turning on, preparing for the next stage of whatever mission brought it here. Leave a like and subscribe to the channel, as tonight we're going to explore the ideas where normal explanations fail and the universe starts to feel strange and unsettling. The real question isn't whether 3I Atlas will leave. It's whether we'll notice if it decides to stay. On July 1st, 2025, Chile's Atlas telescope spotted something amazing. A tiny point of light moving in a way that could only mean one thing. It came from another star system. Named 3I Atlas, formerly C/2025 N0, it became humanity's third confirmed interstellar object after Oumuamua in 2017 and 2I/Borisov in 2019. But what if this third visitor has far bigger implications than the first two? Implications that could change what we think of as a worst-case scenario? Unlike objects from our solar system, which move in predictable elliptical orbits, 3I Atlas follows a hyperbolic path. Its orbit is clearly not bound to the sun coming from the constellation Lyra at incredible speed. It will reach its closest point to the sun on October 29th, moving over 130 miles per hour, fast enough to cross the United States in under 3 minutes. Even though the math makes it look safe, a troubling thought remains. What if the real risk isn't where it's going, but what it might reveal about the universe? Even at this speed, 3I Atlas isn't a threat to Earth. Its closest approach in mid-December will be about 1.8 astronomical units, around 270 million kilometers, almost twice the distance between Earth and Mars. NASA is clear. It's a natural comet, not a spacecraft or dangerous object. But if we step beyond NASA's careful words and imagine what might be possible, this visitor challenges our assumptions about intelligence, purpose, and cosmic coincidence. Since its discovery, the Hubble Space Telescope has observed it behaving like a normal comet. As sunlight heats its surface, ices turn into gas, creating a glowing coma. On August 6th, the James Webb Space Telescope captured spectra showing unusually high levels of carbon dioxide, a mix unlike anything in our solar system. This makes us wonder, could the importance of 3I Atlas lie not in what it is, but in what it tells us about what we don't know? Observatories worldwide have joined the effort. Radio telescopes detect only natural signals, no signs of artificial activity. This global teamwork shows modern astronomy at its best, confirming the object's interstellar origin and safe path. But when we think beyond physical danger and consider ideas that challenge our understanding of our place in the cosmos, fascinating questions appear. Discoveries like this suggest that the galaxy is full of wandering objects, debris from other star systems thrown into space by gravitational forces, drifting for billions of years. Each teaches us more about the galaxy, though none threaten Earth. But if space really is filled with these ancient travelers, what might happen when we imagine beyond what science can confirm? As The Guardian said, 3I Atlas is a cosmic curiosity, not a catastrophe, a reminder that the universe is far stranger and more connected than daily life suggests. This visitor gives us a glimpse into deep galactic history, carrying information from distant stars. But maybe the biggest mystery isn't what it carries. It's what it could reveal about interstellar visitors in general. The numbers are staggering. 3I Atlas moves over 130 miles per hour, about 150 times faster than a rifle bullet. Its hyperbolic excess speed of 61 kilometers per second is the speed it keeps even after factoring in the sun's gravity, unchanged after billions of years in space. But if we imagine possibilities beyond what we can currently measure, what could such high speeds allow? Could this change what we think of as the worst-case scenario? Its speed far exceeds that of previous interstellar visitors. Oumuamua traveled at 26 kilometers per second, and 2I/Borisov at 32 kilometers per second. 3I Atlas moves almost twice as fast, suggesting either a violent ejection from its home system or acceleration through multiple gravitational encounters on its journey. Could this trend of increasing speed hint at something more than random events? Something that pushes our imagination into areas science cannot yet explore? Estimating its size is tricky because the glowing coma hides the core. Current estimates put it between 0.3 and 5.6 kilometers, roughly 3 football fields to a small mountain. Differences come from assumptions about how reflective its surface is and how much gas and dust it produces. Smaller estimates seem more likely, but even at 0.3 kilometers, it's still a serious object. Could the uncertainty about its size point to possibilities beyond just physical measurements? This also raises questions about survival. How could an object of this size survive ejection forces and billions of years in interstellar space? Smaller objects are more easily broken apart by impacts or tidal forces. Could its survival tell us something about strength, durability, or even intentional design? 3I Atlas also seems extremely old. Analysis suggests it comes from the galaxy's thick disk, a population of older stars from when the Milky Way was young. If correct, it predates our solar system by billions of years, holding clues about the galaxy's early history. Could this ancient age be the basis for scenarios that challenge our understanding of time, purpose, and cosmic intelligence? Its unusual path, coming at a strange angle to the galaxy's rotation, suggests it belongs to an older, randomly moving population of stars. These stars have not been smoothed out by billions of years of galactic evolution. Could this unusual angle hint at purpose, navigation, or control beyond normal orbital behavior? Even with its speed and mysterious past, 3I Atlas isn't a physical threat. Its path ensures a safe passage, with closest planetary approaches measured in astronomical units, not kilometers. But the most interesting worst-case scenarios may not involve collision. They may be about what this visitor represents. Observing it is difficult. Its peak brightness is around magnitude 11, needing telescopes even in perfect conditions. At closest approach to the sun, it vanishes in the sun's glare just as it becomes most active. This almost perfect timing could make us miss important details. Could this be a hint that what we cannot see is more important than what we can measure? 3I Atlas represents endurance, ancient, fast, and fleeting. It shows how the universe operates on scales far beyond everyday life, while still following laws precise enough for us to predict its path years in advance. But when we ask what lies beyond these predictable paths, the most intriguing scenarios may not be about physics, but about what this visitor could reveal. When the James Webb Space Telescope observed 3I Atlas on August 6th, it found something remarkable: a coma mostly made of carbon dioxide, with a CO2 to water ratio of about 81. This wasn't just unusual, it was something completely new in comet chemistry. And as we start moving from pure chemical facts into more speculative thinking, What if this molecular pattern hints at origins and purposes that go far beyond what nature alone would create? Most comets follow familiar rules. They're mostly water ice that turns into vapor at modest temperatures, forming the classic gas and dust halo we see. Carbon monoxide shows up next, then carbon dioxide and small traces of other compounds. By comparing these molecular amounts, scientists can tell stories about how and where a comet formed. But 3I Atlas breaks this pattern completely, producing carbon dioxide at levels like nothing we've seen before, almost as if it were being made on an industrial scale. What if this break from the norm opens the door to ideas that challenge what we believe about natural versus artificial origins? The numbers look even stranger when you consider how far away it was. 3I Atlas was more than 3 astronomical units from the Sun, well beyond Mars, when the Webb telescope captured its spectrum. At those distances, most comets barely show any activity. Yet this object was already producing a carbon dioxide-dominated halo stretching hundreds of thousands of kilometers. Could this strange activity at such a great distance point to hidden energy sources, inner mechanisms, or even purposes beyond what we think nature allows? Several natural explanations exist. Maybe 3I Atlas formed near its original star's carbon dioxide snowline, where CO2 built up more than water ice. Or maybe it's so old that cosmic rays changed its surface chemistry, creating a crust that seals in water but lets CO2 escape. Another idea is that it built up a thick blanket of dust over eons, acting like insulation that blocks water but lets more volatile gases seep out. But what if every one of these ideas, no matter how reasonable, misses the most unsettling possibility? That this chemical pattern was deliberately created for reasons we can't yet imagine. Webb's near-infrared spectrograph can detect molecular fingerprints with incredible precision. As sunlight warms the halo, molecules glow at specific wavelengths, revealing exactly what's there. The ratio observed here is one of the strongest carbon dioxide signals ever seen in a comet. But if we push beyond the measurements into speculation, what if these chemical signatures carry information? Not just simple chemistry, but messages or signs of a purpose that challenges our assumptions about intelligence in the universe. This isn't the first time something odd has shown up. Comet C/2016 R2, pan-stars, also showed strange ratios, with unusual levels of carbon monoxide and nitrogen. Such oddities suggest either a wider variety of comet formation conditions than we assumed, or extreme post-formation changes. But as we move closer to pure speculation, what if these chemical outliers hint at a larger pattern? A cosmic signature pointing to possibilities far outside the boundaries of natural explanation. 3I Atlas's real value may be in showing us chemistry from completely different stellar environments. While pan-stars formed under conditions we can model, this visitor carries chemical clues from processes around other stars, possibly billions of years ago. Alien geology delivered right to our doorstep. But what if its arrival wasn't entirely random? And what scenarios open up when we imagine ancient intelligence encoding information into the very chemistry we're now observing? Future observations will tell us whether this carbon dioxide dominance reflects the comet's inner makeup or just its surface. As the sun heats it further, the balance of molecules may change, revealing deeper layers of composition. But what if these changing signatures aren't just the result of random heating but something more like systematic activation? Dormant systems awakening under sunlight. This detective story in chemistry goes beyond 3I Atlas itself. If interstellar objects regularly show exotic compositions, then planet formation around other stars produced far more types of icy bodies than we see here. The carbon-rich environment shaping 3I Atlas might be common around some stars. But as we stand on the edge of speculation, What if these unusual compositions are something more deliberate, markers or signals hinting at a universe filled with intelligences we're only beginning to detect through their chemical fingerprints? From a broader view, this unusual chemistry tests are models of planet formation beyond our solar system. If our theories about icy body formation are correct, they should be able to explain this diversity. 3I Atlas challenges that, suggesting either big gaps in our theories or simply a vast range of conditions in parts of the galaxy we've never studied. But if we go past theory into speculation, what if the challenge this visitor poses to our models is evidence of something deeper, processes, purposes, or intelligences operating beyond the natural laws we've charted? Part 4. The worst case addressed. Nearly 2,000 words into this investigation, the supposed worst-case scenario turns out refreshingly dull. No Hollywood disaster looms. No civilization-ending impact threatens Earth. No hidden gravity well is about to fling our planet into chaos. Cold, precise celestial mechanics deliver a verdict that should help us sleep easy. Yet, as we move beyond the safety of scientific certainty, what if the real worst case lies not in physics but in the shadows of speculation? Places our instruments can't reach and our theories avoid. It's worth repeating the key numbers. 3I Atlas comes no closer than 1.8 astronomical units from Earth, about 270 million kilometers. That's more than twice the distance between Earth and Mars at their closest, and over 50 times farther than the Moon. Perihelion happens around October 29th at about 1.4 astronomical units from the Sun, between Earth and Mars. That's close enough for intense sunlight and a spectacular CO2-rich halo, but nowhere near close enough to disturb planets or shower debris on any world. But what if distance itself doesn't matter when we're thinking about technologies, intelligences, or purposes that don't depend on physical closeness? These aren't rough guesses, but precise orbital calculations accounting for planetary gravity, relativistic effects, and tiny pushes from radiation pressure. When astronomers say 3I Atlas is no threat, they speak with confidence built on centuries of celestial mechanics. Yet what if the calculations that guarantee our physical safety also form the base for more speculative worst cases? Not about collision, but about contact, communication, and cosmic revelation. The initially alarming speed, over 130,000 miles per hour, actually works in our favor. Objects moving that fast on hyperbolic paths can't be captured by the solar system's gravity. 3I Atlas will fly by and head back into interstellar space before it can cause trouble. But what if this very speed, this inability to be captured, isn't just orbital mechanics but deliberate timing and design, a purpose far beyond what we can detect or understand? This raises a key point about how space agencies communicate risk. The term interstellar carries emotional weight that far outweighs actual danger. Our brains react strongly to unknown objects coming from afar, even when the math shows no threat. The reality of space, its vast distances and predictable orbits, makes these encounters more fascinating than dangerous. But what if focusing only on physical danger blinds us to other risks? Scenarios where the worst case isn't what 3I Atlas might do to us, but what it might reveal about us and our place in a far stranger universe. NASA's messaging has been exemplary, balancing scientific importance with a clear statement of no hazard. Simple, jargon-free language explains why this object is remarkable but not threatening, keeping public interest high without sparking fear. Previous interstellar visitors give context. Oumuamua posed no danger in 2017 despite its odd behavior, while 2I Borisov showed standard comet activity in 2019. 3I Atlas follows this pattern of fascinating but harmless visitors. But as we stand on the edge of speculation, What if this pattern of harmless visitors hides something more significant? A kind of cosmic census or a gradual revelation challenging everything we think we know about intelligence, purpose, and our neighborhood in space. Right now, our understanding forms a solid base. We know 3I Atlas's speed, path, and strange CO2-rich composition. We have evidence of great age and an origin deep in the galaxy's thick disk. World-class telescopes have given us detailed measurements of its chemistry and behavior. All of this paints a picture of an ancient, fast-moving, chemically unusual but ultimately natural comet. Yet beneath these comfortable certainties lies the vast unknown. What if the real question isn't just what 3I Atlas is, but what it represents in a universe where intelligence could take forms we've never imagined? Important unknowns remain. Estimates of its size range from hundreds of meters to several kilometers. We don't yet know if its CO2 dominance reflects its core or just its surface. We can't identify its original star or fully map the gravitational encounters that shaped its path. None of these gaps affect our risk assessment. But what if they're the seeds of scenarios far outside natural explanation? This is what proper astronomical risk assessment does. It separates scientific interest from actual threat. Media coverage has mostly reflected this mature approach, stressing both the science and the harmlessness. Visual evidence tells a consistent story. Hubble images show classic comet features, Webb spectra reveal unusual but natural chemistry, and ground-based telescopes track normal gas releases. No artificial signals, no heat signatures, no controlled maneuvers appear in the data. Yet what if this very absence of obvious artificiality is the doorway to speculation about intelligence so advanced and subtle that we can't yet recognize it? Every measurement points to the same conclusion. 3I Atlas is what it seems. A natural comet carrying chemical signatures from alien stellar environments but behaving according to universal physical laws. This confirmation of universality is itself a profound discovery, and the worst-case scenario defined by measurable physical threats is thoroughly ruled out. The math is clear, the observations consistent, the conclusions reassuring. This cosmic visitor comes in peace, intentionally or not. But now we step deliberately beyond the safety of scientific consensus into pure speculation, where worst-case scenarios take different forms, not threats to our safety, but challenges to our understanding of what's possible in a universe that may be far more populated, intelligent, and purposeful than we've yet imagined. Part 5. Alien Tech or Comet. Now we cross that threshold from established fact into speculation, where possibilities multiply like reflections in a hall of mirrors. Everything from here should be seen as a thought experiment, not a scientific conclusion, a mental journey into what if clearly separated from what we actually know. The evidence so far points strongly to 3I Atlas being a natural comet. But what if that evidence is incomplete or misleading? The basic picture stays the same. NASA, the European Space Agency, and almost every major astronomy organization classify 3I Atlas as a natural comet-like visitor. This isn't some kind of groupthink or scientists being cautious just for the sake of it. It's simply the conclusion that best matches the data we have. The object behaves like a typical comet, follows predictable orbital paths, and shows chemical signatures that match ices turning into gas as it gets closer to the sun. Occam's razor, the idea that the simplest explanation is usually the right one, strongly supports the natural explanation here. But science has a long record of surprises. Many of the biggest discoveries have come from objects that at first looked ordinary. Pulsars, for example, were first noticed as strange, highly regular radio signals. For a brief time, they were even labeled LGM, for little green men, before scientists realized they were rapidly spinning neutron stars. Fast radio bursts confused astronomers for years until they turned out to be signals from exotic cosmic processes. Could 3I Atlas be another case where nature turns out to be far stranger than we first assumed? Speculation about it being artificial isn't coming out of nowhere. Avi Loeb, the Harvard astrophysicist who made headlines for his unusual take on the interstellar object Oumuamua, has already floated similar ideas about 3I Atlas in interviews and online posts. Loeb is clear that this is his opinion, not proven fact. His main point is that we should stay open to the possibility that some objects traveling between stars might be technology, not just rocks or ice. This perspective is worth taking seriously, not because it's necessarily true, but because it shows how extraordinary claims should be tested. What kind of evidence would actually prove an artificial origin? What would force scientists to drop the comet idea and accept something much more unusual? These questions matter because they help us separate healthy scientific curiosity from simply brushing off unconventional ideas. If 3I Atlas really were an artificial object, we'd expect to see clear signs that set it apart from natural ones. For example, coherent radio signals might point to built-in electronics or communications. These signals would have to be unmistakably artificial, not random space noise but organized transmissions that natural processes can't produce. Another clue would be changes in its speed or path that don't match the normal behavior of comets. Natural comets sometimes drift a little from their paths because of gases pushing out from their surfaces. But if 3I Atlas started moving in ways that didn't match gas release or solar heating patterns, that could hint at some kind of propulsion. Brightness patterns, or light curves, are another test. Normal comets usually brighten in predictable ways as they near the sun. Their changes match up with how they spin, how their surfaces differ, and how gas escapes. An artificial object might show brightness changes that don't fit those rules, perhaps because it's actively changing its position or exposing different surfaces on purpose. So far, though, none of these artificial signs have been seen in 3I Atlas. Radio telescopes have picked up nothing but silence and the normal emissions expected from icy comet material. This path follows standard gravitational laws without unexplained changes. Its brightness varies in ways astronomers expect from comets. Even its unusual chemical makeup, being rich in carbon dioxide, isn't enough by itself to claim it's artificial. As explained earlier, several natural processes could make a comet like this. Surface radiation effects, formation near certain regions in a young solar system, or insulating dust layers. To jump from chemically unusual to artificially built would take evidence showing no natural process could explain what we see. This is where the lessons from Oumuamua are helpful. That first confirmed interstellar visitor caused a wave of speculation about it being artificial, partly because of its stretched-out shape and its slight extra acceleration. Scientists searched hard for artificial signals and found none. Careful study showed water ice outgassing could explain its strange movement. What seemed extremely weird at first turned out to have natural explanations. The pattern here suggests the best approach to 3I Atlas. Stay open to amazing possibilities but demand equally amazing proof. Science works because it holds all ideas, normal and unusual, to the same strict standards. Claims about artificial origins have to meet those standards, not just point to gaps in what we know. Responsible reporting about this kind of speculation also matters. When news outlets talk about the possibility of 3I Atlas being artificial, they should clearly label it as speculation, not confirmed science. This isn't just an academic detail. It shapes how the public understands both this object and how science itself works. Speculation has a real purpose beyond entertainment. thinking about artificial possibilities makes us examine what truly separates natural from artificial objects in space. It also helps scientists design tests that could, in theory, disprove the comet idea, and it reminds us that the universe may still hold surprises that stretch our understanding. Future observations will keep testing these possibilities. As 3I Atlas gets closer to the Sun, new spectra might reveal chemical clues that are hard to explain naturally. Ultra-precise measurements of its path might show tiny shifts hinting at controlled motion. Long-term monitoring might show behavior patterns that don't fit with passive comet activity. But the burden of proof always stays with those who say it's artificial. The natural comet idea still has the edge because it matches known physics, standard comet behavior, and what we've seen from other interstellar visitors. Overturning that view would take evidence proving natural explanations can't work, and positively showing signs of something built. Even as a natural comet, 3I Atlas is still remarkable. It carries information about stars we've never reached, chemical processes from billions of years ago, and the deep history of our galaxy. That's extraordinary enough without needing an exotic story. And history shows that our greatest breakthroughs often come from careful study of objects that seem ordinary at first. Pulsars, quasars, gamma-ray bursts, and gravitational waves all began as mysterious signals that opened up new physics. Whether 3I Atlas turns out to be a regular comet or something stranger, it's already expanding what we know about the kinds of things that travel between the stars. The next part of this discussion will look at even more dramatic scenarios, not because they're likely, but because they help us explore the kinds of questions that come up when we see something completely new. These mental exercises stretch the boundaries of what's possible while keeping a clear line between speculation and fact, between what we imagine and what we actually know. Now we step into the deepest end of speculation, where the possibilities challenge how we think about our place in the universe. What follows is pure thought experiment, a way to explore what might happen if our assumptions about 3I Atlas turned out to be wrong. The dark forest hypothesis comes from both science fiction and serious discussions about SETI. It takes its name from Liu Cixin's famous novel, but also represents a real idea about how civilizations might behave in the cosmos. It suggests that advanced civilizations could stay deliberately hidden from each other, believing that revealing their presence might attract dangerous attention from more powerful neighbors. In such a universe, staying silent is a survival strategy, and any civilization that announces itself risks destruction from forces it can't detect or understand. If we imagine, and again, this is pure imagination, that 3I Atlas is not a natural comet but a disguised probe, the implications would be staggering. It would mean our solar system is being surveyed by an intelligence able to build objects that travel for billions of years between stars while looking exactly like natural comets. The sheer perfection of its disguise would point to technology far beyond anything we can currently build. Think about what would be required. A probe meant to look like a comet would need to copy every detail of comet behavior. The right chemical signatures, realistic outgassing when warmed by the sun, and surface properties that reflect light just like natural ice and rock. It would have to carry enough icy material to keep up the disguise through its entire trip, all while housing sensors, systems, and communication gear for its real mission. The energy needs alone would be enormous. Keeping systems running across interstellar space for billions of years would require power sources we can hardly imagine. Maybe some kind of long-lasting nuclear generator could work for millennia. Or perhaps advanced fusion systems could run on thin interstellar hydrogen. The probe might even collect energy from cosmic rays or magnetic fields during its journey. But let's take this to its most dramatic point. Imagine our continued observations start to show clear, unexplainable anomalies. Radio telescopes detect short, structured transmissions as the object moves through the outer solar system. This path shows tiny but definite course corrections hinting at active steering. Or maybe its chemical emissions display organized patterns too complex for a random gas release. The real trigger moment in this scenario could come if 3I Atlas begins releasing smaller objects, secondary probes that detach and spread throughout our solar system. One parks itself in orbit around Venus, another near Mars, others at stable gravitational points or in the asteroid belt. Suddenly, our solar system is dotted with a network of unknown devices. The immediate question for humanity would be, how should we respond? This hypothetical event would instantly become the most important diplomatic and strategic challenge our species has ever faced. Unlike the slow, step-by-step first contact stories common in science fiction, the sudden discovery of an active alien surveillance network would force humanity to face the reality of a far more advanced intelligence already observing our solar system. The questions of authority and decision-making would be unlike anything we've ever encountered. Who would speak for Earth? Would it be the United Nations, the leading space agencies, individual nations with spacefaring capabilities, or the scientists who first detected it? Coordinating a global response to something so unprecedented would be a monumental challenge, especially given humanity's often limited track record of international cooperation on even simpler matters. Long-standing debates within the SETI community would immediately take on real-world urgency. For decades, scientists have argued over whether it's safer to broadcast our presence or simply listen for signals from other civilizations. Some warn that sending signals could draw the attention of hostile species, while others point out that a civilization capable of interstellar travel could likely detect our technology no matter how quiet we remain. In this imagined scenario, the choice might no longer be ours. If 3I Atlas and its hypothetical secondary probes were actively monitoring us, every decision we make could become part of the data being collected. Our silence might be read as prudence or fear, while attempts at communication could signal curiosity or even aggression. Even internal debates over how to respond could reveal essential truths about human society to the intelligence observing us. Managing information in such a crisis would be extraordinarily complex. How could leaders inform the public about alien surveillance without causing widespread panic? How could scientists maintain objectivity while acknowledging possibilities beyond current understanding? How could anyone clearly separate verified facts from speculation when the stakes might include the long-term survival of our civilization? Likely, the response would involve expert committees, emergency meetings of scientific organizations, and carefully managed public briefings. Governments would need to balance transparency with stability, giving enough information to maintain credibility while preventing social upheaval. Misinformation would almost certainly spread. Rumors, conspiracy theories, false claims of cover-ups, and sensationalist stories would flood the public sphere. Distinguishing between fact and fiction would be critical to maintaining rational discourse about what could be the most significant discovery in human history. The technological implications of such a scenario would be staggering. If 3I Atlas revealed capabilities beyond our understanding of physics, it could provide insights into propulsion, energy generation, materials science, or communications technology, potentially advancing humanity by centuries. However, the most unsettling aspect of this speculation involves the vast stretches of time. If 3I Atlas had been traveling for billions of years, it could be a relic of a civilization that reached interstellar capability when the Milky Way looked completely different. The intelligence that built it might no longer exist, leaving only automated systems to carry out instructions written long before our sun formed. In this case, we might not be dealing with active alien strategy at all, but with autonomous relics, executing ancient missions with unerring precision. Of course, it must be emphasized repeatedly. Current observations show no evidence supporting this scenario. Every measurement, spectrum, and image continues to confirm the natural comet explanation. 3I Atlas behaves exactly as theory predicts for an interstellar comet. Its unusual chemical makeup fits within known processes, and its path follows physical laws without anomalies. The value of this speculative exercise is not in its likelihood, but in showing how drastically our perspective could shift if our assumptions prove incomplete. The universe has surprised us before, and it will almost certainly do so again. This thought experiment underscores the importance of balancing skepticism with openness to ideas that extend beyond our current understanding. Even now, the real 3I Atlas is an impressive natural object. Ancient, fast, chemically unusual, yet entirely consistent with current science. Whether this understanding will remain sufficient is unknown, but future observations will provide clarity through evidence alone. The concept of the Great Filter tackles one of the deepest questions any advanced civilization can face. If intelligent life is common in the universe, why haven't we seen clear signs of it? First formulated by physicist Enrico Fermi in the 1950s, this question has led to decades of speculation about barriers that might prevent life from arising, advancing, or surviving long enough to spread across the stars. In considering 3I Atlas, we might wonder whether this ancient traveler carries clues from civilizations that faced and failed their own filters. The Great Filter suggests that somewhere along the path from chemistry to starfaring civilization, there is a stage so difficult, rare, or dangerous that almost all attempts fail. It might appear early, in the emergence of self-replicating systems, or much later, when civilizations develop technologies capable of destroying themselves. If 3I Atlas were artificial, its immense age could place its origin billions of years in the past, when our galaxy was a very different place. Did the civilization that launched it survive long enough to see it reach us? The scale of time here is almost unimaginable. Human civilization, from the first farms to today's space programs, spans only around 10,000 years. Recorded history covers roughly 5,000 years, and our technological age barely a few centuries. By contrast, 3I Atlas, if artificial, could embody technology that has endured for millions of times longer than all human history combined. This raises questions about the longevity of technology compared to biological life. Perhaps we would be encountering not active aliens, but the legacy of long-extinct civilizations, autonomous systems executing missions long after their creators vanished. The engineering needed to sustain technology across such spans is staggering. Our most durable human artifacts, pyramids, stone monuments, some isotopes, survive thousands to millions of years. But complex systems like electronics, propulsion, and AI surviving billions of years would require materials far stronger than anything we currently know, energy sources outlasting stars, and software capable of self-repair over unimaginable timescales. A civilization capable of such engineering would have mastered atomic-scale materials, cosmic-level energy, and information processing across eons. Yet if 3I Atlas represents their work, and no other evidence of the civilization remains, what catastrophe, what great filter, might have eliminated them? The possibilities are chilling. Resource depletion on a galactic scale, conflicts with other advanced intelligences, internal collapse due to technological overreach, or unforeseen consequences of environmental or societal pressures. History shows that civilizations often develop technology faster than the wisdom to manage it safely. Humanity faces several such challenges today. Alternatively, the filter might be non-destructive. Highly advanced civilizations could evolve into forms we cannot perceive, uploading consciousness into machines, merging with technology, or moving into dimensions beyond our detection. The scale of the galaxy is staggering. Roughly 400 billion stars, many older than the Sun. Even if only a tiny fraction produced advanced civilizations, the Milky Way could already be thoroughly explored or colonized. Yet the silence persists, a puzzle known as the Fermi paradox. SETI practices reflect this uncertainty, focusing on listening rather than broadcasting, under the assumption that revealing our presence prematurely might be risky. Discovering artificial signatures in 3I Atlas would instantly turn these theoretical concerns into immediate strategic questions. The careful observational frameworks used by astronomers would be crucial in navigating the implications of encountering technology or intelligence far beyond our current understanding. While existing data continues to support the natural comet explanation, entertaining the alternative raises vital questions about long-term survival, technological management, and the trajectory of our own civilization. The Great Filter concept serves both as caution and guidance. It warns that capability does not guarantee survival and inspires careful thought about our development, exploration, and resilience. In this speculative view, 3I Atlas becomes a kind of cosmic relic, a physical testament to a civilization that achieved extraordinary feats, and yet may have ultimately succumbed to forces we can only imagine. The idea of a probe carrying out an ancient mission across the vast stretches of time evokes a striking vision. A machine transporting knowledge from civilizations that mastered interstellar engineering but ultimately failed to navigate the deeper challenges of long-term survival. In this imagined scenario, humanity would find itself as the inheritor of cosmic legacies, tasked with learning from the accomplishments of predecessors while avoiding the mistakes that may have ended their civilization. The stakes would be enormous, touching on nothing less than the survival of our species and our potential to make meaningful contributions to the larger cosmic story. Yet, it must be emphasized that these reflections remain philosophical exercises rather than scientific conclusions. In reality, 3I Atlas continues to behave precisely as we expect from a natural comet. Its motion is governed by gravity and physics, not conscious intention. Whether this understanding will remain sufficient is uncertain, but future observations and careful evidence will provide answers. As we wander further into speculative territory, it becomes increasingly important to distinguish between imagination and evidence. The universe, even governed solely by natural processes, is already profoundly strange. From the bizarre behavior of quantum particles to the mysterious acceleration of cosmic expansion, and the intricate web-like structure of galaxies across the cosmos, nature alone offers more than enough wonder. Introducing intelligent design or alien intent, while intriguing, may not be necessary to appreciate the universe's complexity and majesty. This question resonates across every corner of astronomy, shadowing the search for extraterrestrial intelligence and haunting every moment we gaze into the night sky and encounter only emptiness. It was famously posed by Enrico Fermi during a casual discussion in 1950, but the question's significance has only deepened as we have explored more of the universe. If the Milky Way is filled with intelligent life, if life is common and capable of developing civilizations, then why have we found no clear signs of it? Interstellar objects like 3I Atlas add a new dimension to this paradox. Each visitor from another star system offers a natural experiment, a sample of matter from distant regions of the galaxy. In theory, such objects could carry traces of advanced civilizations, engineered materials, unusual isotope ratios, or structured shapes revealing intelligent design. Yet, every confirmed interstellar visitor observed so far appears entirely natural. This absence of artificial markers may offer clues about the behavior of advanced civilizations. Perhaps highly developed societies deliberately avoid detection, sending probes so cleverly disguised that they mimic natural objects perfectly? If so, the most advanced technology would be the hardest to notice. This raises immediate questions about detection. If 3I Atlas were an intentionally concealed probe, what would allow us to recognize it? The distinction between natural and artificial phenomena might be far subtler than we currently understand. Narrowband radio emissions are the clearest signature of technology. Natural sources produce a wide range of radio frequencies, while engineered signals concentrate energy in specific, easily identifiable bands. SETI has searched for such signals for decades, assuming that any civilization capable of interstellar communication might produce detectable electromagnetic patterns. To date, 3I Atlas has remained silent in the radio spectrum, emitting only the expected signals from natural cometary activity interacting with the solar wind. No coherent transmissions or modulated signals have been detected. While this supports the natural comet hypothesis, it cannot entirely rule out the existence of more advanced concealment technologies. Thermal behavior offers another potential clue. Objects in space naturally heat and cool according to the sunlight they absorb, radiating energy in predictable ways. Artificial constructs, by contrast, might maintain unusual heat distributions, internal energy sources, or asymmetric thermal patterns inconsistent with solar input. Observations of 3I Atlas in infrared light show behavior fully consistent with natural processes. Its temperature rises smoothly as it nears the sun, and the variations across its surface reflect topography and composition rather than deliberate thermal control. Maneuvering patterns would provide the most decisive evidence of artificial origin. While comets experience small, random changes in velocity from outgassing, intentional propulsion would reveal controlled, sustained trajectory adjustments. 3I Atlas, however, follows the smooth, hyperbolic path predicted by gravity, with minor variations fully explained by solar radiation and natural outgassing forces. If it has any propulsion, it is either inactive or too subtle to detect. From a broader perspective, the existence of natural interstellar objects aligns with our understanding of planetary system formation. Models predict that young stars eject significant amounts of rocky and icy debris through gravitational interactions with planets. Many small bodies are flung into interstellar space before they can develop into fully formed worlds. The stream of visitors like Muamua, 2I Borisov, and 3I Atlas fits perfectly within these theoretical expectations. As detection methods improve, interstellar objects will likely shift from rare curiosities to regularly observed phenomena. The upcoming Vera Rubin Observatory, beginning operations soon, should find several per year, providing the large statistical samples needed to understand their origins. This perspective offers a potential resolution to Fermi's paradox regarding interstellar objects. Natural debris may vastly outnumber artificial probes, making detection of alien technology akin to finding a needle in a galactic haystack. 3I Atlas's unusual CO2-rich composition further highlights the diversity of materials ejected from different stellar systems. What may initially appear unusual, or even suspiciously artificial, might actually represent the normal variety of planetary formation processes across the galaxy. Survey biases also shape our interpretations. Current ground and space-based observations preferentially detect objects from certain directions, with specific brightness or orbital characteristics. The first interstellar objects we observed may not represent the broader population, just as the earliest exoplanet discoveries were biased toward hot Jupiters. 3I Atlas's approach from southern skies challenged expectations and revealed gaps in our models, suggesting either incomplete understanding of object distributions or significant scattering of trajectories by gravitational encounters. Looking ahead, future observations will dramatically expand our understanding. The Vera Rubin Observatory's decade-long survey will detect hundreds of interstellar objects, enabling rigorous statistical analysis of their properties, origins, and orbital paths. Infrared space telescopes will probe their thermal behavior and chemistry in unprecedented detail. Over time, this data will either confirm that these wanderers follow natural patterns predicted by planetary formation models, or reveal anomalies that demand more exotic interpretations. If advanced probes exist among the interstellar population, such observations should eventually expose subtle but persistent differences between engineered objects and naturally occurring bodies. The continuing absence of clear artificial signatures has profound philosophical implications. Every natural interstellar visitor strengthens the idea that civilizations capable of interstellar engineering may be exceedingly rare, undetectable, or intentionally hidden. Each observation of cosmic solitude reminds us of the vast unknowns. Yet lack of evidence is not proof of absence. Our detection capabilities remain limited, and our current sample of interstellar visitors is still extremely small. The universe may still hold phenomena that challenge our assumptions about intelligence, technology, and the detectable traces of both across the cosmos. Whether 3I Atlas is a naturally occurring interstellar visitor or something engineered, it represents another piece in humanity's ongoing quest to understand its place within the vast cosmic landscape. As we push further into speculative scenarios, the distinction between observable reality and imaginative extrapolation becomes increasingly vital. The cosmos, as revealed through meticulous observation and rigorous analysis, is already remarkable and strange, offering enough wonder on its own. Whether or not it hosts other forms of intelligence remains an open question, one that future discoveries and evidence will answer with the impartial clarity only careful science can provide. Now we enter the outermost reaches of speculative imagination, where the boundary between plausible science and cinematic storytelling blurs. Here, the scenarios we imagine stretch the limits of physical principles, yet remain tethered just enough to known physics to inspire wonder. Picture the most extreme possibility. 3I Atlas is not merely a probe or spacecraft, but a delivery system for something far subtler and more insidious. Embedded within its icy body could be microscopic devices, or perhaps engineered biological agents, which we might call microseeds, lying dormant, awaiting precise environmental triggers. These could be nanotechnological constructs engineered to endure the harsh extremes of interstellar space over billions of years, or biological systems designed to propagate across star systems via exactly this mechanism. Though wildly speculative, the idea echoes aspects of existing scientific hypotheses. The panspermia hypothesis, while still controversial, proposes that life may naturally spread across the galaxy through comets, asteroids, or other interstellar debris. Some researchers suggest that hardy microorganisms could survive exposure to cosmic radiation, vacuum, and deep space cold for millions or even billions of years, seeding new planets when conditions become favorable. Our cinematic scenario, however, goes far beyond passive panspermia. These microseeds would be engineered not only to survive the interstellar journey, but to remain inert until encountering very specific triggers. Perhaps activation would respond to the electromagnetic signatures of technological civilizations, radio transmissions, industrial pollution, or other markers of intelligence. Alternatively, they might awaken in response to stellar radiation patterns, activating only when the host object passes stars of certain spectral classes. The engineering challenges implied are immense. These microscopic constructs would need to remain structurally intact despite cosmic radiation, collisions with interstellar dust, and extreme thermal fluctuations over billions of years. power sources would have to function far longer than the lifetimes of most stars. Information storage would require resistance to molecular decay over geological or even galactic timescales. Ideally, they would be capable of using raw planetary materials to bootstrap complex systems upon arrival. If such technology were possible, the strategic implications would be extraordinary and terrifying. A single interstellar object like 3I Atlas could potentially carry trillions of these dormant microseeds, each capable of establishing itself on any suitable world it encounters. The invasion, if it could be called that, would be silent, incremental, and invisible until activation. The trigger might not occur until centuries or millennia after 3I Atlas passes through our solar system. Perhaps the microseeds are programmed to activate only once humanity reaches particular technological milestones, population densities, or environmental markers. Such a delay would allow detailed reconnaissance of human civilization, ensure that activation occurs under optimal conditions, and obscure the connection between the original delivery and the eventual response. Yet even in this imaginative exercise, reality imposes severe constraints. The extreme conditions endured by 3I Atlas during its interstellar journey present nearly insurmountable obstacles for any technology or life form. Cosmic radiation alone would degrade molecular structures over millions of years, making survival across billions of years exceedingly unlikely. The comet's own outgassing adds further hazards. As volatile ices sublimate, they violently eject dust and other embedded material, a process repeated with every solar encounter over eons. Even if microseeds survived all of this, the vast distances involved, hundreds of millions of kilometers at closest approach, would further dilute their density, making successful deposition on Earth extraordinarily improbable. Current planetary protection protocols, designed to prevent contamination of Earth and other celestial bodies, provide a useful framework for thinking about such speculative scenarios. These involve strict containment, biosafety lab analysis, and careful evaluation of any potentially novel biological or technological materials. Yet these protocols assume direct sample return missions, not the passive capture of microscopic particles distributed across interplanetary space. Detecting such microseeds would be a staggering challenge. Searching for objects engineered to remain dormant for centuries among trillions of dust particles would be akin to finding needles in a haystack the size of the solar system. Radar or optical surveys, even at their most advanced, could not reliably track microscopic material on such scales. This brings us to a critical flaw in the silent invasion hypothesis. It is grossly inefficient. Any civilization capable of engineering technology capable of surviving billions of years in deep space would likely have far more reliable and direct methods to achieve the same strategic goals. Direct communication, conventional spacecraft, or other observable interventions would be simpler and far more effective. Nevertheless, the scenario serves an important purpose in our speculative exploration. It illustrates how human imagination can stretch far beyond the bounds of practical reality when confronted with the unknown. It also underscores the distinction between healthy scientific caution and unwarranted fear. In our treatment of such ideas, clear disclaimers are essential. This is speculation, not evidence, a mental exercise in exploring extremes rather than describing likely realities. Meanwhile, the real story of 3I Atlas remains elegant and comprehensible. Its behavior aligns perfectly with expectations for a natural comet. Predictable dust ejection, thermal patterns consistent with solar heating, and chemical signatures entirely explicable by known astrophysical processes. No exotic hypotheses are required to account for its properties. As we conclude this speculative journey, it is worth reflecting on what such thought experiments reveal about human psychology. Our inclination to imagine dramatic scenarios, alien probes, silent invasions, hidden technologies, reflects both our creativity and our deep-seated desire to comprehend our place in a vast, often indifferent universe. Yet the natural three-eye atlas, traveling across interstellar space at incredible speed, is astonishing enough on its own. This ancient visitor brings chemical clues from distant worlds, providing a fleeting glimpse into the history and complexity of our galaxy. That reality alone offers ample cause for wonder and investigation, without invoking hidden technologies or cinematic invasions. Ultimately, exploring these possibilities, however improbable, sharpens our understanding of both the universe and the limits that physics, evidence, and reason place on credible explanation. Speculation reminds us why rigorous observation matters, why extraordinary claims require extraordinary evidence, and why the natural cosmos, strange, beautiful, and ancient, remains more than capable of inspiring awe. The global response to Three-Eye Atlas has exemplified the most admirable qualities of human scientific collaboration. A carefully choreographed dance of telescopes, observatories, institutions, and researchers all working in synchrony to extract the maximum knowledge from a fleeting visitor. Within hours of the object's discovery by the Atlas survey on July 1, 2025, a worldwide network of observatories was already mobilized, demonstrating that modern astronomy operates as a genuinely international enterprise. The immediate response followed established protocols developed over decades of asteroid and comet observation. The Minor Planet Center at Harvard-Smithsonian served as the central hub for astrometric data, gathering position measurements from observatories across the globe and refining orbital calculations with every new observation. Europe's Space Situational Awareness Program added its own tracking resources, while NASA's Planetary Defense Coordination Office evaluated any potential impact risk, quickly ruling out collision. But the interstellar nature of Three-Eye Atlas demanded attention beyond routine procedures. Space telescopes were reprioritized. Hubble and James Webb both shifted to study this unprecedented visitor. Webb focused on spectroscopic analysis of the comet's unusual carbon dioxide-rich coma, while ground-based observatories, from Chile's Atacama Desert to Hawaii's Mauna Kea, contributed complementary multi-wavelength observations. This seamless coordination illustrates how rapidly modern astronomy can respond, a sharp contrast to earlier eras when discoveries might linger in notebooks for months before verification. Information sharing has been remarkably transparent. NASA and ESA have published regular updates, offering both detailed technical data and accessible summaries for the public. Popular astronomy publications have supplemented these updates with observing guides for amateurs eager to glimpse the interstellar traveler. Now, imagine a scenario far beyond our current observations. Suppose future data revealed signatures inconsistent with natural processes, coherent radio emissions, deliberate trajectory changes, or the deployment of secondary objects within the solar system. How would humanity respond to what might become the most consequential discovery in history? Existing structures provide some guidance. The International Astronomical Union has protocols for verifying extraordinary claims, requiring independent confirmation from multiple observatories. The SETI Institute maintains guidelines for potential first contact, covering information sharing, public communication, and international coordination. Planetary protection procedures, developed over decades, address risks posed by alien microorganisms or exotic life forms. Yet none of these frameworks were designed for active extraterrestrial technology within the solar system. Coordination would need to scale to unprecedented levels. Jurisdictional questions would emerge immediately. Which international body governs first contact? How do nations reconcile scientific curiosity with security concerns? Political stakes would be enormous. Confirmation of alien technology would instantly become a matter of national security, forcing military and intelligence agencies to confront the reality of non-human intelligence potentially superior to our own. Technical hurdles would be equally daunting. Current spacecraft cannot reach the outer solar system on interstellar timescales. Any meaningful interaction with a fast-moving object like 3I Atlas would likely be limited to radio transmission, assuming we could recognize or decode alien protocols. Humanity's reach remains confined to the solar neighborhood, with transit times measured in years rather than months. Public communication would present a monumental challenge. Announcing evidence of alien intelligence without triggering panic or mass hysteria would require careful balancing of tone and timing. Lessons from past events, such as the 1977 WOW signal and the brief speculation surrounding Oumuamua, underscore the importance of distinguishing between provocative observations and verified conclusions. The 24-hour news cycle and social media would amplify uncertainty, making the clear communication of verified results essential to maintaining public trust. The economic and societal implications would be profound. Markets would react to the sudden emergence of revolutionary science. Entire industries might face existential disruption if alien technology offered alternatives to energy, transportation, or manufacturing. Educational and research institutions would confront the need to reframe curricula and research priorities to account for the existence of non-human intelligence. Philosophical and theological questions would ripple across disciplines, forcing a re-examination of humanity's place in the cosmos. Time would be a pressing constraint. Unlike slowly approaching celestial phenomena, interstellar visitors adhere to the immutable schedules dictated by physics. Decisions and actions might need to unfold within months rather than years, compressing deliberation and testing institutional resilience. Yet the actual response to 3I Atlas has demonstrated remarkable efficiency. Within weeks, the global astronomical community had identified the object, confirmed its interstellar trajectory, coordinated multi-wavelength observations, and begun rigorous analysis. This track record suggests that existing institutions, while imperfect, provide a robust foundation for dealing with unprecedented phenomena. Theoretical frameworks developed over decades, including SETI protocols, astrobiological guidance, and international legal scholarship, offer valuable starting points for rapid decision-making under extraordinary circumstances. Above all, the response has emphasized curiosity over fear, collaboration over secrecy, and rigorous investigation over speculation. Transparency in sharing observational data and open cooperation represent humanity's best approach to cosmic mysteries. These qualities form a template for how civilization can engage with the unknown, whether or not alien contact is ever confirmed. Human exploration has always navigated the tension between curiosity and caution, from crossing oceans to climbing mountains to venturing into space. In the case of 3I Atlas, this balance decisively favors curiosity. Its trajectory and properties preclude meaningful containment, while offering maximal scientific opportunity. Planetary protection frameworks, developed to safeguard Earth from alien life and other worlds from terrestrial contamination, provide a useful conceptual reference. They were designed for direct sample return missions or close spacecraft encounters, not for distant, high-velocity interstellar visitors showing no evidence of biological activity. The underlying principle is risk assessment proportional to potential harm. For example, Mars samples collected by the Perseverance rover are subject to extraordinary precautions to prevent accidental release of hypothetical microorganisms. Spacecraft targeting Europa or Enceladus undergo strict sterilization to avoid contaminating these environments. 3I Atlas presents a fundamentally different scenario. Its closest approach, 1.8 astronomical units, roughly 270 million kilometers, prevents any direct material exchange with Earth. No interception is feasible, and the object's extreme speed eliminates the possibility of capture. Containment, in practical terms, becomes academic. This safe distance has enabled an unusually open scientific approach. Hubble images, Webb spectroscopic data, and ground-based observations have been shared freely through archival databases, allowing researchers worldwide to analyze identical datasets and verify conclusions. This transparency exemplifies the scientific method. Multiple independent investigators examining the same evidence and converging on consistent interpretations, in this case confirming the object's natural origin. The open archive culture surrounding major space telescopes deserves particular recognition. Platforms like the Mikulski Archive democratize access to Hubble and Webb data for anyone with an internet connection, while European Southern Observatory archives support ground-based observations. Amateur astronomers contribute through citizen science platforms, producing additional datasets and light curves. This culture of openness contrasts sharply with the secrecy that would likely characterize military or intelligence responses to hypothetical alien contact. The scientific community's default toward transparency reflects both practical necessity and a philosophical commitment to shared knowledge. Peer review lies at the heart of scientific practice, demanding both rigorous data sharing and a philosophical commitment to the universal nature of knowledge. The investigation of 3I Atlas exemplifies how these principles function even when confronting phenomena that might, in principle, represent humanity's first encounter with extraterrestrial intelligence. The rapid dissemination of information surrounding 3I Atlas highlights both the benefits and challenges of instant global communication. Professional networks allow legitimate scientific results to propagate almost in real time, enabling collaboration among researchers separated by continents. Yet these same channels also carry misinformation, speculation, and sensational misinterpretations that can distort public understanding. Social media algorithms, optimized for engagement rather than accuracy, often amplify dramatic claims and conspiracy theories at the expense of measured scientific analysis. Distinguishing between genuine scientific uncertainty, the kind that drives productive research, and unfounded speculation has become increasingly critical for maintaining rational public discourse on cosmic discoveries. 3I Atlas serves as a compelling case study in these dynamics. Mainstream scientific sources have consistently emphasized the object's unusual properties while confirming its natural origin, acknowledging uncertainty without resorting to sensationalism. Less reputable sources have sometimes exaggerated preliminary findings, conflated speculation with fact, or promoted conspiracy theories about alien cover-ups. Visual communication adds another layer of complexity. Dramatically processed Hubble and Webb images, while scientifically informative, can appear otherworldly to general audiences. Presenting these images in a context that emphasizes scientific meaning, demonstrating come-try behavior rather than alien technology, is essential to maintaining accurate public understanding. The question of containment extends beyond physical material to the realm of information. Should certain astronomical discoveries be classified or restricted? The scientific community has generally answered no. Open collaboration has proven more beneficial than any hypothetical security gained through restricted access. Practically, astronomy thrives as a global enterprise, with researchers sharing data, verifying results, and building collective understanding. Philosophically, the view from space has long reminded humanity of its shared cosmic heritage, offering unity rather than division. Historical precedents support this approach. Pulsars, initially nicknamed LGM, Little Green Men, ultimately revealed new physics rather than alien intelligence. The 1977 WOW signal, though unexplained, was carefully documented and analyzed in public forums. Even the peculiarities of Oumuamua were examined through international collaboration rather than classified research. Citizen science further exemplifies the curiosity over containment principle. Amateur astronomers contributed images and light curves that complemented professional observations, enriching the scientific dataset and democratizing research in ways that would be impossible under restrictive policies. Next-generation missions promise to expand these capabilities. The FAREX mission could map 3I Atlas's extended carbon dioxide coma, while wide-field infrared surveys like SphereX will complement Webb's detailed spectroscopy, producing a comprehensive portrait of interstellar visitors. The Vera Rubin Observatory's legacy survey of space and time will detect hundreds of such objects, enabling statistically robust studies that either confirm natural distributions or reveal anomalies demanding more exotic explanations. The rapid coordination, transparent data sharing, and emphasis on international collaboration demonstrated in the 3I Atlas case provide a template for future discoveries. This experience also underscores the importance of balancing skepticism and openness. Extraordinary claims require extraordinary evidence, yet scientists must remain receptive to possibilities that exceed current understanding. 3I Atlas demonstrates how to maintain this balance, acknowledging unusual properties while resisting unfounded speculation. Its safe passage through the solar system, behavior consistent with natural comet physics, and absence of anomalous signatures establish a baseline for evaluating future interstellar objects. Deviations from this pattern may warrant new approaches, but the default assumption remains that natural explanations should be exhausted before entertaining more exotic possibilities. The journey that brought 3I Atlas to our cosmic doorstep spans distances and timescales almost beyond comprehension. Understanding these scales is crucial for appreciating both the object's significance and our place within galactic evolution. If 3I Atlas originates from the thick disk of the Milky Way, it carries material formed 10 to 12 billion years ago, in an era when the galaxy was chaotic and young. Stars in the thick disk follow eccentric, tilted orbits, remnants of violent formation processes, unlike the orderly circular orbits of the thin disk, where our Sun resides. The object's nucleus thus preserves a chemical record of stellar neighborhoods that existed long before our solar system even began. The timescales involved are staggering. If 3I Atlas has been wandering the galaxy for 5 billion years, a conservative estimate based on its presumed thick disk origin, it has traveled for over 1,000 times longer than complex life has existed on Earth. During its voyage, our planet witnessed the Cambrian explosion, 5 mass extinctions, the rise and fall of dinosaurs, and the emergence of human civilization. From the object's perspective, all of human history represents a mere fraction of a cosmic instant. Distances are equally mind-boggling. Even at velocities exceeding 130,000 miles per hour, traversing significant portions of the galaxy requires millions of years. Along the way, 3I Atlas likely encountered hundreds or thousands of stellar systems, occasionally perturbed by their gravitational fields, silent flybys occurring far from observers capable of recording them. The cumulative effect of these interactions may account for the object's extreme velocity, naturally accelerating it without the need for exotic propulsion. This chemical composition provides an additional layer of insight. Rich in carbon dioxide, the object likely formed in a stellar environment very different from our Sun's. It offers a tangible sample of alien chemistry, preserving isotopes, minerals, and volatiles that reveal conditions in distant stellar neighborhoods billions of years ago. This form of chemical archaeology extends our understanding of galactic evolution in ways that conventional astronomical observation cannot replicate. By contrast, humanity's own radio presence is tiny on a galactic scale. Since Marconi's first wireless transmissions, our radio signals have expanded outward at light speed, reaching only about 120 light-years, just a fraction of the Milky Way's roughly 100,000 light-year diameter and a few thousand out of an estimated 400 billion stellar systems. Even deliberate interplanetary communications would appear as faint whispers to any distant listeners. The idea that 3I Atlas could have been drawn to our solar system by these signals is implausible given both its immense age and the limited reach of our broadcasts. This perspective also reframes the Fermi paradox. The apparent silence of the cosmos is less surprising when set against galactic distances. Even if thousands of civilizations were transmitting, their signals would weaken dramatically with distance. The inverse square law ensures that doubling the separation reduces signal strength by a factor of 4, making interstellar communication an immense technical challenge, even for civilizations far more advanced than ours. Energy considerations further constrain interstellar activities. Broadcasting a detectable signal across typical galactic distances would require power outputs comparable to small stars. Accelerating even a small probe to interstellar speeds demands energy on the scale of entire nations' annual production. In contrast, 3I Atlas achieved its extreme velocity naturally through repeated gravitational interactions, a testament to the galaxy's ability to accelerate objects over cosmic timescales. This natural mechanism provides a compelling, non-exotic explanation for the object's high speed. Perhaps the most profound gift 3I Atlas offers humanity lies not in exotic speculation about its origins, but in the simple fact of its non-threatening passage through our cosmic neighborhood. In an era when global challenges can feel overwhelming, there is something deeply reassuring about a cosmic visitor that arrives precisely as predicted, obeys natural laws flawlessly, and departs safely into the interstellar night without disturbing a single terrestrial sunset. This reassurance is far from trivial. It represents the triumph of scientific understanding over cosmic anxiety, the victory of careful observation over unfounded speculation. When 3I Atlas was first detected, racing toward our solar system at unprecedented velocity, uncertainty might have inspired fear. Yet within weeks, international teams of astronomers had calculated its trajectory, analyzed its chemical composition, and confidently predicted its harmless passage. A testament to human knowledge, cooperation, and technological capability at their finest. The scientific harvest from 3I Atlas has already exceeded what most astronomical discoveries yield over entire lifetimes. Its unusual carbon dioxide-rich composition challenged assumptions about comet chemistry, prompting researchers to refine models of volatile distribution in objects formed around different stellar environments. Spectroscopic signatures captured by the James Webb Space Telescope reveal chemical processing around distant stars, including high CO2 to H2O ratios in the coma, suggesting formation near CO2 snowlines or long-term radiation processing. These insights extend far beyond cometary science, refining our understanding of planetary formation and evolution and informing the search for habitable worlds in the galaxy. The institutional response has demonstrated the efficiency of modern astronomical coordination. The Atlas survey detected the object. The Minor Planet Center orchestrated global tracking. Hubble and Webb provided detailed follow-up, while ground-based observatories contributed complementary observations, all within weeks. Beyond technological capability, this coordination reflects a philosophical commitment to shared knowledge and collaborative investigation. The decision to make observational data publicly available underscores the conviction that cosmic discoveries belong to humanity as a whole. Transparency has proven essential, both for scientific rigor and public engagement. Open data allow amateur astronomers, students, and citizen scientists to contribute meaningfully to monitoring 3I Atlas. This democratization of research stands as one of modern astronomy's most encouraging trends. At the same time, careful communication has been vital to counter misinformation and sensationalism. Social media amplifies dramatic claims, but consistent messaging from scientific institutions, coupled with patient correction of misunderstandings, ensures rational public discourse. Speculation about exotic scenarios, while captivating, gains value only when tied to evidence. Considering the improbable encourages researchers to test the limits of natural explanations, devise falsifiable hypotheses, and remain open to surprises. Yet the true triumph of 3I Atlas lies in demonstrating that extraordinary discoveries do not require extraordinary fear. Through observation, analysis, and collaboration, humanity has illuminated the deep workings of an object that is ancient, chemically distinctive, and yet fundamentally natural. Looking ahead, the Vera Rubin Observatory promises to transform interstellar objects from rare curiosities into statistically significant populations, enabling studies of chemical diversity, dynamics, and galactic evolution. The unusual CO2 signatures of 3I Atlas may prove typical of early-generation objects or remain uniquely exotic, but either way, they provide a tangible connection to the broader processes shaping our galaxy. In every sense, 3I Atlas exemplifies science at its best. Imaginative yet disciplined, collaborative yet rigorous, speculative yet evidence-driven. It replaces fear with understanding, revealing the profound rewards of patient observation and careful inquiry. As 3I Atlas continues its ancient voyage outward from our sun, fading daily into the star-scattered darkness from which it came, we are left with images that will endure long after the object itself disappears beyond the reach of our most powerful telescopes. Hubble's exquisite portraits show a fuzzy, star-like point enveloped in the gossamer glow of its carbon dioxide coma, a cosmic ornament suspended against the infinite black. Webb's infrared vision reveals the molecular signatures of the coma with precise clarity, each spectral line a word in the ancient chemical language carried from its birthplace around another star. Trajectory plots tell their own story. Smooth arcs tracing 3I Atlas's passage through the solar system, skimming past Mars's orbit, swinging around the Sun at perihelion, and continuing outward toward the gas giants before venturing once again into interstellar space. These curves are a cosmic choreography written in gravitational motion, a silent dance spanning millions of years and billions of miles. Through careful observation, coordinated investigation, and patient analysis, humanity has witnessed the fleeting presence of a messenger from another star. Its story is one of chemical archaeology, cosmic perspective, and the quiet power of scientific inquiry. And though 3I Atlas now recedes into the dark, the knowledge it leaves behind endures, a reminder of our ability to understand, to explore, and to find hope in the vast silence of the universe. These aren't the chaotic, unpredictable paths of human politics or economics, but the serene precision of celestial mechanics, inevitable as sunrise, dependable as the seasons. There is something deeply satisfying in this predictability, this cosmic reliability that operates entirely beyond human influence. While our terrestrial world churns with uncertainty, 3I Atlas follows laws that have governed motion in space since the universe began. Its departure is scheduled not by human decision, but by the fundamental forces that shape reality itself. In an age dominated by manufactured anxiety and artificial urgency, such cosmic dependability offers profound comfort. The answer to our investigation's central question, the worst-case scenario, has proven refreshingly mundane. No Hollywood catastrophe awaits. No alien invasion threatens our civilization. No cosmic disruption will alter Earth's orbit or climate. In terms of actual physical threat, the answer is nothing at all. 3I Atlas will leave our solar system exactly as it arrived. Silently, safely, and according to the precise predictions of physics. Yet calling this outcome mundane misses its true significance. That we can predict the behavior of an object that has traveled billions of years, formed around a star we've never observed, and carries chemical signatures from environments we've never studied. This is one of science's greatest triumphs. Physics operates with such consistency that phenomena separated by cosmic distances and geological time follow the same fundamental rules. The strangeness revealed by 3I Atlas remains no less fascinating for being natural. Its carbon dioxide-rich chemistry challenges assumptions about typical comet composition, expanding our understanding of materials that form around different types of stars. Its apparent thick-disk galactic origin provides a sample of ancient chemistry from stellar environments far removed from our solar neighborhood. These unusual properties have already shaped how astronomers think about planetary formation, cometary evolution, and the diversity of interstellar objects. Research papers on 3I Atlas will inform decades of study, its lessons woven into broader theories about icy bodies throughout the galaxy. Speculative scenarios involving alien technology, ancient civilizations, or exotic physics have served their purpose in exercising our imagination, but evidence consistently points toward natural explanations. Remarkable as they are, these phenomena operate entirely within our current understanding of physical law. The universe has proven strange and wonderful enough through natural processes alone, from quantum mechanics to black holes to cosmic expansion. Adding exotic technology is unnecessary to inspire awe and a cosmic perspective. The music accompanying our farewell to 3I Atlas should be neither ominous nor triumphant, but contemplative. Holst's The Planets or Barber's Adagio for strings. Compositions that evoke the vastness of space while maintaining human emotional resonance. The tone invites reflection rather than excitement, wonder rather than fear. Throughout this investigation, we've maintained clear boundaries between established science and imaginative speculation, marking where data ends and conjecture begins. This transparency reflects intellectual honesty and practical necessity in an era when misinformation spreads faster than corrections can arrive. The final message is not about threats or invasions, but the subtler danger of cosmic anxiety, the fear that arises when confronted with phenomena beyond our immediate understanding. 3I Atlas demonstrates that such fears can be dispelled through patient observation, careful analysis, and international collaboration committed to evidence-based understanding. Epilogue cards could guide viewers to publicly available resources that made this investigation possible. NASA's official pages, the Space Telescope Science Institute archives with Hubble and Webb data, professional journals, and popular astronomy publications. These resources embody the democratic spirit that has characterized the 3I Atlas investigation from the start. Openness in data sharing represents a philosophical commitment to knowledge that transcends borders, offering hope for future interstellar discoveries. The Ryuban Observatory will detect dozens of similar objects in the coming decade, each with its own lessons about galactic chemistry, planetary formation, and the wandering population of interstellar space. Some may prove chemically more unusual than 3I Atlas. Others may challenge our understanding in entirely new ways. Each discovery will enrich the growing database of interstellar objects, enabling statistical studies that reveal the distribution of materials, dynamics, and chemical diversity across the galaxy. Credits acknowledging observatories, archives, and individual researchers are more than formalities. They remind us that scientific discovery emerges from collaboration, not isolated genius. Coordination among ground-based surveys, space telescopes, and data archives enabled rapid characterization of this interstellar visitor, demonstrating modern astronomy at its most effective. As 3I Atlas fades into the cosmic distance, propelled by momentum accumulated over its billion-year interstellar journey, it leaves behind more than data and papers. It leaves a case study in how human civilization approaches the unknown, with instruments rather than weapons, curiosity rather than fear, collaboration rather than competition. These choices reflect our highest aspirations for engaging with cosmic mysteries that may prove even more profound than this ancient wanderer. The silence following 3I Atlas's departure is not empty, but expectant, waiting for the next cosmic messenger, carrying its own chemical secrets, ancient histories, and challenges to our understanding. In that waiting, in our continued watching of the skies, lies the most hopeful aspect of humanity's relationship with the cosmos. The conviction that wonders remain to be discovered, questions yet to be asked, and reasons to look up with curiosity rather than fear. The gentle fade to black accompanies 3I Atlas as it blends back into the stellar backdrop. Not a distinct object, but once again part of the cosmic landscape. Its passage through our solar system lasted mere months in a journey spanning geological ages, and we were privileged to witness this brief moment, study this ancient traveler, and add its story to the catalog of wonders in interstellar space. Good night, cosmic messenger. Thank you for the lessons, the data, and the reminder that the universe remains far stranger and more wondrous than our earthbound imaginations might suggest. Safe travels on your continued journey, carrying the chemical secrets and ancient memories locked within your nucleus, testimony to stellar environments that existed long before our world knew the warmth of its star. Until we meet your cousins from other distant systems, other epochs, other corners of the cosmic wilderness surrounding our remarkable planetary home.